You're observing an interstellar visitor, three-eye atlas, a mysterious object drifting between the stars. Its light, its reflection, maybe even its electromagnetic whisper carries thousands of frequencies. But we believe one of them, one faint, narrow tone, could be special. Perhaps it's the resonance of a mineral that can heal the body, or a harmonic that could bring peace to Earth. To find it, we need more than a telescope. We need mathematics and hardware. We need a digital down converter. We start with a receiver sampling at 500 megahertz, fast enough to capture every shimmer up to 100 megahertz. Our incoming signal is a mix of three cosmic tones at 10, 37, and 85 megahertz, each with its own random phase, like three overlapping voices in the interstellar choir. Space is never silent. Cosmic background, instrument electronics, and thermal motion all add noise. We simulate that with Gaussian noise at a signal to noise ratio of 20 dB. So our raw measurement, y equals x plus noise, looks as messy and alive as a real telescope bead. Using MATLAB's P-Welch method, we estimate the power spectral density, the energy of the cosmos versus frequency. You'll see three peaks glinting through the noise floor. Those are our possible songs of three-eye atlas. And because of conjugate symmetry of real signals, we get the image, the digital twins to the left. Now we're going to tune the receiver. We multiply by a 10 megahertz local oscillator. That is our magic frequency. That's the frequency that we want. And this shifts the entire cosmic chorus down in frequency. Now the new tones appear at 0, 20, 27, 47, 75, and 95 megahertz. The same music, just translated into our baseband frame. Baseband is our 0 megahertz. This is how we tune in to the precise region where the universe may be whispering to us. Now we need to quiet the noise. We apply a 2 megahertz low pass filter to keep only the slow central vibration, the one that could hold our minerals' resonance and suppress the rest. After filtering, the higher harmonics fade away, leaving a clean heartbeat of the cosmos. Zooming in, with the bandwidth narrowed, we can safely downsample by 50, slowing our digital heartbeat from 500 megahertz to 10 megahertz. Now the view zooms to plus or minus 5 megahertz, focusing on the narrow region around DC or baseband. You won't see the blue trace from the original wideband signal anymore, not because it's gone, but because those tones at 10, 37, and 85 megahertz now lie far outside our zoomed in window. What remains is the faint glow of our candidate tone, our special tone. Look closely. There's a tiny bump near 3 megahertz. It's not a new discovery yet. It's residual energy from the 27 megahertz component leaking through the finite low pass filter and aliasing after downsampling. In real systems, even spacecraft, this happens all the time. Imperfect rejection, folded echoes of stronger signals. To quiet them, we can design steeper filters or use higher order finite impulse responses. This comes at a cost. With more multiplications and additions, which are resources on the FPGA. So we can sharpen our ear to the cosmos, but at a cost of mathematical resources on our real-time hardware, the FPGA. And that's what digital downconversion truly is, the act of tuning in. Mathematically, it's mixing, filtering, and decimating. It's listening for harmony hidden inside chaos. Maybe that single tone from 3i Atlas is just physics, or maybe it's a vibration meant to remind us of balance between technology and nature, signal and noise, the self and the universe. If this resonates with you, hit like and subscribe and leave me a note sharing where you're from. Until next time, have a peaceful day.